Greetings, AP Chemistry students. Today, I'm going to talk with you about some more with equilibrium, and we're going to actually talk about the equilibrium constant itself. So, the equilibrium position for any reversible chemical reaction that achieves a state of equilibrium is described by an equilibrium constant Kc, or sometimes it's just symbolized with K. Now, please note, this is a capital letter K, unlike the lowercase k for the rate constant. Now, this is related to the rate constant because, as you'll see, essentially, in some way, the equilibrium constant is kind of like the rate constant of the reverse reaction divided by the rate constant of the forward reaction, but it's not exactly that. But just like your rate constant, the equilibrium constant is temperature dependent. Equilibrium constants do not, however, have units. For rate constants, figuring out what the units are was an essential part of solving a kinetics problem. But equilibrium constants, they don't have units. Well, technically they do have units, but the units all cancel out, and so they're not significant. So we just ignore the units. Now, in order to write an equilibrium expression, we need to use the law of mass action, which says that for any reaction, let's see here. Law of mass action says for any reaction with reactants A and B and products C and D with coefficients represented by the lowercase a's, b's, c's, and d's, your equilibrium expression says that K equals the concentration, square brackets mean concentrations or essentially molarities, the concentrations of your products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients. Now, in case you forget this formula is on your reference tables, so you do not have to memorize it. Now, if you reverse a chemical reaction, in other words, you're switching the products and the reactants, then that would change what goes on top and what goes on the bottom. So if you reverse a reaction, the K of your reverse reaction is 1 over the original value of K. If you multiply a reaction by a factor n, so for instance, if we multiplied all of our coefficients by some value, then our new value of K equals K to the power of n. And if you add two reactions together, you multiply the values of K. So let's consider the following reactions. So if we consider this first reaction where nitrogen plus 3 hydrogens makes 2 NH3s, it's going to have some value of K. And our equilibrium expression would say that K equals the concentration of NH3 squared over the concentration of N2 times the concentration of H2 squared, cubed. For the second reaction, whatever our original value of K was equal to, the new value of K equals 1 over our original value of K. And for this reaction, which is the first reaction reversed and doubled, our new value of K is 1 over K squared, because we've doubled the reaction, so we would square the value of K. Or in other words, it would equal, our new value of K would equal the concentration of N2 squared times H2 to the 6th divided by NH3 to the 4th. Right? Now, there's also Kp that is used sometimes instead of Kc, because Kc is used for molarities or concentrations. Kp is used for partial pressures. So if we use partial pressures instead of concentrations, we use Kp. where Kp equals the partial pressures of those things. Now, let's take a look back at this example. If we wanted to write a Kp for this first reaction, Kp would equal the partial pressure of NH3 squared divided by the partial pressure of nitrogen times the partial pressure of hydrogen cubed. And you need to make sure that with KPs, you're using parentheses with these exponents and not square brackets. If what you write appears to be square brackets when you should be using parentheses, then your answer will be counted as incorrect. Now, a few more things to point out about these equilibrium constants. Pure solids and pure liquids are not included in the equilibrium expression. They are left out because the concentration or molarity of a liquid does not change. It's constant. It only depends on the density. So things whose concentrations don't change, we don't put them in our equilibrium expression. So let's consider a question you've probably never examined closely before. What is the molarity of water? Well, molarity equals moles over liters. So in order to calculate the molarity, we need to pick some moles and or we need to pick some liters. Let's keep things fairly simple. Let's say we're talking about 1 liter of water. Well, 1 liter of water is 1,000 grams. And then we can convert grams into moles, where 1 mole is 18.016 grams. And so we take 1,000 divided by 18.016, and the molarity, or the moles, are 55.5. So the molarity of water is 55.5 molar. That's a very useless piece of information. It doesn't really mean very much to us. But the thing is that that's based off of the density of water. That for every 1 liter of water, there's 1,000 grams. So no matter how much water you have, its molarity is 55.5. So when we're doing equilibrium calculations, we don't include liquid water in it. We also don't include solids. So let's say we're writing an equilibrium expression for the dissolving of magnesium iodide. It dissolves to make magnesium with a +2 charge plus 2 I minuses. And these are aqueous. Well, the equilibrium expression would say that K equals the concentration of the magnesium ions times the concentration of the iodide ions squared divided by, well, there's nothing to divide it by because this is a solid. We don't include it in our equilibrium expression. So this would be the equilibrium expression. Similarly, there's another example that you may have seen before. If we're talking about water, we know that water, as a liquid, it can make H pluses and hydroxides. And so the K for this equals the concentration of H plus times the concentration of OH minus. We don't include the liquid water. This is a very special K, as we'll see when we get to our unit on acids and bases, called Kw. And I happen to know its value. It's 1 times 10 to the negative 14th. That happens to be the equilibrium constant. It's equal to that number at 25 degrees Celsius. Right? So once again, for both Kp and Kc expressions, we do not include pure solids or pure liquids. We only include gases and For KCs, we would include things that are dissolved in water. KP and KC are not equal to each other. They do not have the same value unless there's a very specific set of circumstances that apply, which we're not going to worry about in this class. And we're not going to worry about how do you convert from KC to KP and vice versa. If you're referring to KP, it's always spelled out as KP. For KC, sometimes they just call it K and they leave out the C. But for KPs with pressures, it's always specified with the P. Now let's just look at a few more things here. A few more properties of K. If K is a very large number, then that essentially means the reaction proceeds almost completely to completion. If K is a very small number, that implies that the reaction barely occurs at all. It mostly lies over at the reactant side. So that means that based on the magnitude of the equilibrium constant, we can determine how far this reaction goes. In the case of this equilibrium expression, K equals 1 times 10 to the negative 14th, which is an incredibly small number. So this reaction does not happen very much at all. It mostly stays as pure water. Most water molecules in a sample of liquid water do not break apart into H pluses and OH minuses. They stay as liquid water. For this one with magnesium iodide, which is incredibly soluble, we would expect that K is quite large. K is much larger than 1. By the way, just in case you haven't figured this out yet, since we're plugging in pressures or molarities, these are always positive numbers, so K can never be less than 0. K can never be a negative number. It can be really large, it can be really small, but it cannot go negative. If you find yourself dealing with negative numbers, you've made a mistake. So let's consider the following problem, where A plus 2B makes AB2. At equilibrium, we have the following concentrations. This is 3.7 if you can't read that. What is the value of K? Well, K equals products over reactants. So it's AB2 divided by A times B squared. And so that's going to equal 3.7 divided by 0.15 times 0.18 squared. And so if we put this into a calculator, 3.7 divided by 0.15 times 0.18 squared, that equals 761. Now let's see, does this make sense? Well, if K is large, 761 is quite a bit larger than a lot of numbers. It's significantly greater than 1, let's just say. So in that case, what this means is that we have a lot of products, not a lot of reactants at equilibrium. And we'll notice the amount of our product, 3.7, is quite a bit larger than the amount of our reactants. So this does kind of make sense. Let's consider one more thing. If we had started with equal amounts of both A and B, when equilibrium is established, what can we say about the relative amounts of A and B? Well, this reaction is going to proceed to the right because K is a quite large number. And so as A is used up, B gets used up twice as fast. So whenever we establish equilibrium, the amount of A is going to be quite a bit larger than the amount of B. But the amount of AB2, this product, is going to be even larger than either of those. Since K is quite large, this reaction will go significantly to the product side. But as A gets used up, B gets used up twice as fast. So at equilibrium, A would be less than the concentration of A would be less than the concentration of AB2, but the concentration of B would be even less because B gets used up twice as quickly. So I hope that makes a little bit of sense to you. And with that said, I hope y'all have a great day.